Introduction to Web Security Consideration. In this video, we are going to see about Introduction to Web Security Consideration. The World Wide Web is fundamentally a client-server application running over the Internet and TCP/IP intranets. The Internet is two-way. Unlike traditional publishing environments, even electronic publishing systems involving teletext, voice response, or fax back, the web is vulnerable to attacks on the web servers over the Internet. The web is increasingly serving as a highly visible outlet for corporate and product information and as a platform for business transactions. Web browsers are very easy to use. Web servers are relatively easy to configure and manage. Web content is increasingly easy to develop. The underlying software is extraordinarily complex. This complex software may hide many potential security flaws. Casual and untrained, that is, in security matters, users are common clients for web-based services. Such users are not necessarily aware of the security risks that exist and do not have the tools or knowledge to take effective countermeasures. Web security threats. In this video, we are going to see about what is web security threats. There are few types of security threats faced when using the web. Threats, consequences, countermeasures. Integrity, threats, modification of user data, Trojan horse browser, modification of memory, modification of message traffic in transit. Consequences, loss of information, compromise of machine, vulnerability to all other threats. Countermeasures, cryptographic checksums. Confidentiality, threats, eavesdropping on the net, theft of information from server, theft of data from server, info about network configuration, info about which client talks to server. Consequences, loss of information, loss of privacy. Countermeasures, encryption, web proxies, denial of service. Threats, killing of user threats, flooding machine with bogus requests, filling up disk or memory, isolating machine by DNS attacks. Consequences, disruptive, annoying, prevent user from getting work done. Countermeasures, difficult to prevent. Authentication, threats, impersonation of legitimate users, data forgery. Consequences, misrepresentation of user, belief that false information is valid. Countermeasures, cryptographic techniques. One way to group these threats is in terms of passive and active attacks. Passive attacks include eavesdropping on network traffic between browser and server and gaining access to information on a website that is supposed to be restricted. Active attacks include impersonating another user, altering messages in transit between client and server, and altering information on a website. Another way to classify web security threats is in terms of the location of the threat, web server, web browser, and network traffic between browser and server. Issues of server and browser security fall into the category of computer system security. Web traffic security approaches. In this video, we are going to see about the process of web traffic security approaches. A number of approaches to provide web security are possible. The various approaches that have been considered are similar in the services they provide and to some extent in the mechanisms that they use, but they differ with respect to their scope of applicability and their relative location within the TCP/IP protocol stack. Network level. One of the ways to provide web security is by using the IP security, IPsec. The advantage of using IPsec is that it is transparent to end users and applications and provides a general purpose solution. IPsec includes a filtering capability so that only selected traffic need incur the overhead of IPsec processing. Transport level. Another relatively general-purpose solution is to implement security just above TCP. The foremost example of this approach is Secure Sockets Layer (SSL) and the follow-on Internet standard known as Transport Layer Security (TLS). At this level, there are two implementation choices. For full generality, SSL or TLS could be provided as a part of the underlying protocol suite and therefore be transparent to applications. SSL can be embedded in specific packages. For example, Netscape and Microsoft Explorer browsers come equipped with SSL, and most web servers have implemented the protocol. Application level. Application-specific security services are embedded within the particular application. The advantage of this approach is that the service can be tailored to the specific needs of a given application. Secured Socket Layer. Now, let us see about what is Secured Socket Layer. The Secured Socket Layer (SSL) is the most widely deployed security protocol used today. It is essentially a protocol that provides a secure channel between two machines operating over the Internet or an internal network. In today's Internet-focused world, the SSL protocol is typically used when a web browser needs to securely connect to a web server over the inherently insecure Internet. SSL is a transparent protocol which requires little interaction from the end user when establishing a secure session. In the case of a browser, for instance, users are alerted to the presence of SSL when the browser displays a padlock, or in the case of Extended Validation SSL, when the address bar displays both a padlock and a green bar. This is the key to the success of SSL. It is an incredibly simple experience for end users. Extended Validation (EVSSL) certificates such as Global Sign Extended SSL display visible trust indicators. The address bar turns from white to green, indicating to visitors the website is using Extended Validation SSL. The website owner's legally incorporated company name is displayed prominently on the address bar. Real estate Extended Validation SSL is the only way for a company to get its name displayed in the browser address bar. The standard HTTP is changed to HTTPS, automatically telling the browser that the connection between the server and the browser must be secured using SSL. The padlock is activated, showing that the browser connection to the server is now secure. If there is no padlock or the padlock shows a broken symbol, the page does not use SSL. Standard SSL certificates such as Global Sign Domain SSL and Organization SSL display. The standard HTTP is changed to HTTPS, automatically telling the browser that the connection between the server and the browser must be secured using SSL. The padlock is activated, showing that the browser connection to the server is now secure. If there is no padlock or the padlock shows a broken symbol, the page does not use SSL. as opposed to unsecured HTTP URLs which begin with http:// and use port 80 by default. Secure HTTPS URLs begin with https:// and use port 443 by default. HTTP is insecure and is subject to eavesdropping attacks which, if critical information like credit card details and account logins is transmitted and picked up, can let attackers gain access to online accounts and sensitive information. Ensuring data is either sent or posted through the browser using HTTPS is ensuring that such information is encrypted and secure. SSL used in today's modern server society. To secure online credit card transactions, to secure system logins and any sensitive information exchanged online, to secure webmail and applications like Outlook, Web Access, Exchange and Office Communications Server, to secure workflow and virtualization applications like Citrix delivery platforms or cloud-based computing platforms, to secure the connection between an email client such as Microsoft Outlook and an email server such as Microsoft Exchange, to secure the transfer of files over HTTPS and FTPs services such as website owners updating new pages to their websites or transferring large files, to secure hosting control panel logins and activity like Parallels, cPanel, and others, to secure intranet-based traffic such as internal networks, file sharing, extranets, and database connections, to secure network logins and other network traffic with SSL VPNs such as VPN access servers or applications like the Citrix Access Gateway. SSL architecture. In this video, we are going to see about architecture of SSL. The transport layer security is layered on top of the transport layer such as TCP. The protocol is composed of two layers, the TLS record layer and the TLS handshake layer. The TLS handshake layer consists of the handshake protocol, the alert protocol, the change cipher spec protocol, and the application data protocol. The orange box with the HTTP1 layer and TLS record layer combined constitutes Hypertext Transfer Protocol Secured HTTPS. If HTTP1 layer is replaced with FTP, the orange box will be the File Transfer Protocol Secure FTPS. Of course, HTTP2 outside of the orange box is the plain HTTP without any security support. Handshake and protocol flow. Here is a flow of the protocol between a client and a server. The client sends a client hello message to the server. A client hello message contains the following information. Protocol version, the version of the TLS protocol by which the client wants to communicate during this session. Random, a random structure which contains the current time and date and 28 bytes of a secure random number generated by the client. Session ID, the ID of a session the client wishes to use for this connection. Cipher suite, the cipher suite list which contains the combinations of cryptographic algorithms supported by the client. Compression method, a list of compression algorithms supported by the client. The server responds with a server hello message in response to a client hello message if it was able to find an acceptable algorithm. A server hello message contains the following information. Protocol version. The version of the TLS protocol by which the server agrees to communicate with the client during this session. Random. A random structure which contains the current time and date and 28 bytes of a secure random number generated by the server. Session ID. The ID of a session the server wishes to use for this connection. Cipher suite. The single cipher suite selected by the server from the list of the cipher suite contained in the client hello message. Compression method. The single compression algorithm selected by the server from the list of the compression method contained in the client hello message. Immediately after the server sends a server hello message to the client, it sends a server certificate message and a server key exchange message to the client. The certificate request message can optionally be sent by the server to request a certificate from the client if the server chooses to authenticate the client. Then the server sends a server hello done message and will wait for a client to respond. The client sends a client certificate message to the server if the server requests a certificate in response to the server hello done message. Immediately after the client certificate message is sent, a client key exchange message and a certificate verify message are sent by the client. The client sends a certificate verify message for the server to verify a client certificate. If the server does not request a certificate, the client key exchange message will be the first message sent by the client. A change cipher spec message and a finished message are sent by the client. In response, the server will send a change cipher specification message and a finished message. At this point, the client and server can exchange application layer data. Transport layer security. In this video, we are going to see about transport layer security. S-Channel supports versions 1.0, 1.1 and 1.2 of the Transport Layer Security TLS protocol. This protocol is an industry standard designed to protect the privacy of information communicated over the Internet. TLS assumes that a connection-oriented transport, typically TCP, is in use. The TLS protocol allows client-server applications to detect the following security risks: message tampering, message interception, message forgery. Organization of TLS. The following steps are involved in using TLS for client-server communication: Handshake and Cipher suite negotiation, authentication of parties, key-related information exchange, application data exchange. The steps that makes up the TLS to be divided into two protocols that, together, provide connection security: TLS Handshake Protocol, TLS Record Protocol. TLS Handshake Protocol. In this video, we are going to see about the working process of TLS Handshake Protocol. The Transport Layer Security TLS Handshake Protocol is responsible for the authentication and key exchange necessary to establish or resume secure sessions. When establishing a secure session, the Handshake Protocol manages the following: Cipher suite negotiation, authentication of the server and optionally the client, session key information exchange. Cipher suite negotiation. The client and server make contact and choose the cipher suite that will be used throughout their message exchange. Authentication. In TLS, a server proves its identity to the client. The client might also need to prove its identity to the server. PKI, the use of public-private key pairs, is the basis of this authentication. The exact method used for authentication is determined by the cipher suit negotiated. Key exchange. The client and server exchange random numbers and a special number called the pre-master secret. These numbers are combined with additional data, permitting client and server to create their shared secret called the master secret. The master secret is used by client and server to generate the right MAC secret, which is the session key used for hashing, and the right key, which is the session key used for encryption. Establishing a secure session by using TLS. The TLS handshake protocol involves the following steps. The client sends a client hello message to the server, along with the client's random value and supported cipher suits. The server responds by sending a server hello message to the client, along with the server's random value. The server sends its certificate to the client for authentication and may request a certificate from the client. The server sends a server hello done message. If the server has requested a certificate from the client sends it. The client creates a random pre-master secret and encrypts it with a public key from the server's certificate, sending the encrypted pre-master secret to the server. The server receives a pre-master secret. The server and client each generate the master secret and session keys based on the pre-master secret. The client sends change cipherspec notification to the server to indicate that the client will start using the new session keys for hashing and encrypting messages. Client also sends client finished message. Server receives change cipherspec and switches its record layer security state to symmetric encryption using the session keys. Server sends server finished message to the client. Client and server can now exchange application data over the secure channel they have established. All messages sent from client to server and from server to client are encrypted using session key. Resume a secure session using TLS. The client sends a client hello message using the session ID of the session to be resumed. The server checks its session cache for a matching session ID. If a match is found and the server is able to resume the session, it sends a server hello message with a session ID. If a session ID match is not found, the server generates a new session ID and the TLS client and server perform a full handshake. Client and server must exchange change cipherspec messages and send client finished and server finished messages. Client and server can now resume application data exchange over the secure channel. TLS record protocol. In this video, we are going to see about TLS record protocol. The Transport Layer Security TLS record protocol secures application data using the keys created during the handshake. The record protocol is responsible for securing application data and verifying its integrity and origin. It manages the following: dividing outgoing messages into manageable blocks and reassembling incoming messages, compressing outgoing blocks and decompressing incoming blocks, optional, applying a message authentication code MAC to outgoing messages and verifying incoming messages using the MAC, encrypting outgoing messages and decrypting incoming messages. When the record protocol is complete, the outgoing encrypted data is passed down to the Transmission Control Protocol (TCP) layer for transport. Secured Electronic Transaction (SET). In this video, we are going to see about what is Secured Electronic Transaction (SET). Secured Electronic Transaction (SET) is a system for ensuring the security of financial transactions on the Internet. It was supported initially by MasterCard, Visa, Microsoft, Netscape, and others. With SET, a user is given an electronic wallet, that is digital certificate, and a transaction is conducted and verified using a combination of digital certificates and digital signatures among the purchaser, a merchant, and the purchaser's bank in a way that ensures privacy and confidentiality. SET makes use of Netscape's Secure Socket Layer (SSL), Microsoft Secure Transaction Technology (STT), Teresa Systems Secure Hypertext Transfer Protocol (SHTTP). SET uses some but not all aspects of a public key infrastructure (PKI). Process of SET. Assume that a customer has a SET-enabled browser such as Netscape or Microsoft's Internet Explorer, and that the transaction provider, that is bank, store, etc., has a SET-enabled server. The customer opens a MasterCard or Visa bank account. Any issuer of a credit card is some kind of bank. The customer receives a digital certificate. This electronic file functions as a credit card for online purchases or other transactions. It includes a public key with an expiration date. It has been through a digital switch to the bank to ensure its validity. Third-party merchants also receive certificates from the bank. These certificates include the merchant's public key and the bank's public key. The customer places an order over a web page, by phone, or some other means. The customer's browser receives and confirms from the merchant's certificate that the merchant is valid. The browser sends the order information. This message is encrypted with the merchant's public key, the payment information, which is encrypted with the bank's public key, which can't be read by the merchant, and information that ensures the payment can only be used with this particular order. The merchant verifies the customer by checking the digital signature on the customer's certificate. This may be done by referring the certificate to the bank or to a third-party verifier. The merchant sends the order message along to the bank. This includes the bank's public key, the customer's payment information, which the merchant can't decode, and the merchant's certificate. The bank verifies the merchant and the message. The bank uses the digital signature on the certificate with the message and verifies the payment part of the message. The bank digitally signs and sends authorization to the merchant, who can then fill the order. Dual signature. Now we are going to learn about dual signature. The purpose of the dual signature is to link two messages that are intended for two different recipients. In this case, the customer wants to send the order information OI to the merchant and the payment information PI to the bank. The merchant does not need to know the customer's credit card number, and the bank does not need to know the details of the customer order. To see the need for the link, suppose that the customer sends the merchant two messages, a signed OI and a signed PI, and the merchant passes the PI on to the merchant bank. If the merchant can capture another OI from this customer, the merchant could claim that this OI goes with a PI rather than the original OI. The figure shows the use of a dual signature to meet the requirement of a preceding paragraph. The customer takes the hash using SHA1 of the PI and the hash of the OI. These two hashes are then concatenated and the hash of the result is taken. Finally, the customer encrypts the final hash with his or her private signature key, creating the dual signature. The operation can be summarized as follows. DS is equal to EKRC of H of PI equally divides H of OI, where KRC is the customer's private signature key. Now suppose that the merchant is in possession of the dual signature DS, the OI, and the message digest for the PI, PIMD. The merchant also has the public key of the customer taken from the customer's certificate. Then the merchant can compute the following two quantities. H of PIMD equally divides H of OI and DKUC of DS, where KUC is the customer's public signature key. If these two quantities are equal, then the merchant has verified the signature. Similarly, if the bank is in possession of DS, PI, the message digest for OI, OIMD, and the customer's public key, then the bank can compute the following. H of PI equally divides OIMD and DKUC of DS. Again, if these two quantities are equal, then the bank has verified the signature. For example, suppose the merchant wishes to substitute another OI in this transaction to its advantage. It would then have to find another OI whose hash matches the existing OIMD. With SHA1, this is deemed not to be feasible. Thus, the merchant cannot link another OI with this PI. Secured Mail and Pretty Good Privacy (PGP). In this video, we are going to see about Secured Mail and Pretty Good Privacy (PGP). Secured Mail. In virtually all distributed environments, electronic mail is the most heavily used network-based application. Users expect to be able to send email to others who are connected directly or indirectly to the internet, regardless of host operating system or communication suite. With the explosively growing reliance on email, there grows a demand for authentication and confidentiality services. Two schemes stand out as approaches that enjoy widespread use: Pretty Good Privacy (PGP) and S/MIME. Pretty Good Privacy (PGP). Pretty Good Privacy (PGP) is a popular program used to encrypt and decrypt email over the internet. It can also be used to send an encrypted digital signature that lets the receiver to verify the sender's identity and know that the message was not changed en route. PGP is the most widely used privacy ensuring program by individuals and is also used by many corporations. Developed by Philip R. Zimmermann in 1991, PGP has become a standard for email security. PGP can also be used to encrypt files being stored so that they are unreadable by other users or intruders. Services. PGP provides a confidentiality and authentication service that can be used for electronic mail and file storage applications. In essence, what Zimmermann has done is the following. Selected the best cryptographic mechanisms, that is algorithms, as building blocks. Integrated these algorithms into a general purpose application that is independent of operating system and processor, and that is based on a small set of easy to use commands. made the package and its source code freely available via the internet, bulletin boards, and commercial networks such as America Online (AOL). Entered into an agreement with a company via CryptNow Network Associates to provide a fully compatible, low-cost commercial version of PGP. From its beginnings about 15 years ago, PGP has grown explosively and is now very widely used. A number of reasons are cited for such growth. It is available free worldwide in versions that run on many different platforms: Windows, Unix, Mac, etc. In addition, the commercial version satisfies those who want Windows support. It is based on algorithms that have survived extensive public review and are considered secure. Specifically, the package includes RSA, DSS, and Diffie-Hellman for public key encryption, CAST128, IDEA, and 3DES for symmetric encryption, and SHA for hash coding. It has a wide range of applicability, from corporations that wish to select and enforce a standardized scheme for encrypting files and messages to individuals who wish to communicate securely with others worldwide over the internet. It was not developed by, nor it is controlled by, any government or standards organization. For those with an instinctive distrust of the establishment, this makes PGP attractive. In the last few years, commercial versions have become available. PGP is now on an Internet Standards Track RFC 3156. Operational description. In this video, we are going to see about operational description of PGP. PGP consists of the following 5 services: authentication, confidentiality, compression, email compatibility, segmentation. The table explains a summary of these services and algorithms used to implement them. Operational description. Function: digital signature, message encryption, compression, email compatibility, segmentation. Digital signature. Algorithms used: DSS, SHA, or RSA, SHA. Description: a hash code of a message is created using SHA-1. This message digest is encrypted using DSS or RSA with the sender's private key and included with the message. Message encryption. Algorithms used: CAST or IDEA or 3-key triple DES with Diffie-Hellman or RSA. Description: a message is encrypted using CAST128 or IDEA or 3DES with a one-time session key generated by the sender. The session key is encrypted using Diffie-Hellman or RSA with the recipient's public key and include with a message. Compression. Algorithms used: zip. Description: a message may be compressed for storage or transmission using zip. Email compatibility. Algorithms used: radix 64 conversion. Description: to provide transparency for email applications, an encrypted message may be converted to an ASCII string using radix 64 conversion. Segmentation. Algorithms used: none. Description: to accommodate maximum message size limitations, PGP performs segmentation and reassembly. Authentication. In this video, we are going to see about authentication. The hash function used is SHA-1, which creates a 160-bit message digest. EPDP represents public encryption, decryption, and the algorithm used can be RSA or DSS. The message may be compressed using an algorithm called ZIP. This is represented by Z in the figure. The combination of SHE1 and RSA provides an effective digital signature scheme. Due to the strength of RSA, the recipient is assured that only the possessor of the matching private key can generate the signature. Because of the strength of SHE1, the recipient is assured that no one else could generate a new message that matches the hash code and hence the signature of the original message. Confidentiality. In this video, we are going to see about confidentiality. Another basic service provided by PGP is confidentiality, which is provided by encrypting messages to be transmitted or to be stored locally as files. In both cases, the user has a choice of cast 128, IDEA or DDES in 64-bit cipher feedback CFB mode. The symmetric key is used only once and is created as a random number with the required number of bits. It is transmitted along with a message and is encrypted using the recipient's public key. The given figure illustrates the sequence. The sender generates a message and a random number to be used as a session key for this message only. The message is encrypted using cast 128, IDEA or DDES with a session key. The session key is encrypted with the RSA or another algorithm known as LGAMAL using the recipient's public key and is prepended to the message. The receiver uses RSA with its private key to decrypt and recover the session key. The session key is used to decrypt the message. The public key encryption is a lot more computationally intensive than symmetric encryption. For this reason, both forms are used as public key encryption solves the key distribution problem. However, as will be noticed, the message itself, which is the largest part of the transmission, is encrypted using symmetric key cryptography, whereas only the key is encrypted using the public key algorithm. Confidentiality and authentication. The figure illustrates both services may be used for the same message. First, a signature is generated for the plaintext message and prepended to the message. Then the plaintext message plus signature is encrypted using cast 128 or IDEA or DDES and the session key is encrypted using RSA or LGAMAL. This sequence is preferable to the opposite, encrypting the message and then generating a signature of the encrypted message. It is generally more convenient to store a signature with a plaintext version of a message. Furthermore, for purposes of third-party verification, if the signature is performed first, a third party need not be concerned with a symmetric key when verifying the signature. Compression. In this video, we are going to see about compression. PGP compresses the message after applying the signature but before encryption. This has the benefit of saving space both for email transmission and for file storage. The placement of the compression algorithm, indicated by Z for compression and Z-1 for decompression in the figure, is critical. The signature is generated before compression for two reasons. It is preferable to sign an uncompressed message, so it is free of the need for a compression algorithm for later verification. Different versions of PGP produce different compressed forms. Applying the hash function and signature after compression would constrain all PGP implementation to the same version of the compression algorithm. Message encryption is applied after compression to strengthen cryptographic security because the compressed message has less redundancy than the original plain text. Cryptanalysis is more difficult. Email compatibility. In this video, we are going to see about email compatibility. Many electronic mail systems only permit the use of blocks consisting of ASCII text. When PGP is used, at least part of the block to be transmitted is encrypted. This basically produces a sequence of arbitrary binary words in which some mail systems won't accept. To accommodate this restriction, PGP uses an algorithm known as radix 64, which maps 6 bits of a binary data into an 8-bit ASCII character. Unfortunately, this expands the message by 33%. However, with a compression algorithm, the overall compression will be about 1/3 in general. Segmentation. In this video, we are going to see about segmentation. Email facilities are often restricted to a maximum message length. For example, many of the facilities accessible throughout the internet impose a maximum length of 50,000 octets. Any message longer than that must be broken up into smaller segments, each of which is mailed separately. To accommodate this restriction, PGP automatically subdivides a message that is too large into segments that are small enough to send via email. The segmentation is done after all the other processing, including the radix 64 conversion. Thus, the session key component and signature component appear only once at the beginning of the first segment. At the receiving end, PGP must strip off all email headers and reassemble the entire original block before performing the steps illustrated in the figure. S/MIME. In this video, we are going to see about what is S/MIME. After the development of PEM Industry Working Group led by RSC Security Incorporation started to develop another specification for conveying digitally signed and/or encrypted and digitally enveloped data in accordance to the MIME message formats. S/MIME, that is Secure or Multipurpose Internet Mail Extension, is a security enhancement to the MIME Internet Email Format Standard. S/MIME is not restricted to mail. It can be used with any transport mechanism that transports MIME data such as HTTP. S/MIME is likely to emerge as an industry standard for commercial and organizational use, while PGP will remain the choice for personal email security for many. S/MIME provides the following cryptography security services: authentication, message integrity, and non-repudiation of origin or by using digital signing. Privacy and data security or by using encryption. MIME Overview. RFC 822 defines a format for text messages that are sent using electronic mail. SMTP or RFC 822 scheme limitations are: SMTP cannot transmit executable files or other binary files. SMTP cannot transmit text data that includes national language characters because these are represented by 8-bit codes with values of 128 decimal or higher, and SMTP is limited to 7-bit ASCII. SMTP servers may reject mail message over a certain size. SMTP gateways that translate between ASCII to EBCDIC suffer translation problems. Some SMTP implementations do not adhere completely to the SMTP standard defined in RFC 822. MIME specification includes the following elements: 5 new message header fields. These fields provide information about the body of the message. A number of content formats are defined, thus standardizing representations that supports multimedia email. Transfer encodings are defined that protect any content format to be altered by the mail system. MIME provides a standardized way of dealing with a wide variety of information representations in a multimedia environment. The other major component of MIME is the definition of transfer encodings for message contents. 7 bits. The data are all represented by short lines of ASCII characters. 8 bits. The lines are short, but there may be non-ASCII characters, that is, octets with high-order bit set. Binary. Not only may non-ASCII characters be present, but the lines are not necessarily short enough for SMTP transport. Coded printable. Encodes the data in such a way, if the data being encoded are mostly ASCII text, the encoded form of the data remains largely recognizable by humans. Base 64. Encodes data by mapping 6 bits blocks of input or output, all of which are printable ASCII characters. X token, a named non-standard encoding. S/MIME functions. In this video, we are going to learn about S/MIME functions. S/MIME is based on the cryptographic message syntax CMS specified in RFC 2630. Enveloped data. This consists of encrypted content of any type and encrypted content encryption keys for one or more users. This function provides privacy and data security. Signed data. A digital signature is formed by signing the message digest and then encrypting that with the signer private key. The content and the signature are then encoded using base 64 encoding. This function provides authenticity, message integrity, and non-repudiation of origin. Clear signed data. As with signed data, a digital signature of the content is formed. However, in this case, only the digital signature is encoded using base 64. As a result, recipients without S/MIME capability can view this message content, although they cannot verify the signature. Signed and enveloped data. Signed only and encrypted only entities may be nested so that encrypted data may be signed and signed data or clear signed data may be encrypted. Cryptographic algorithms. Function requirements. Create a message digest to be used in forming a digital signature. Must support SHA-1. Receiver should support MD5 for backward compatibility. Encrypt message digest to form a digital signature. Requirements. Sending and receiving agents must support DSS. Sending agents should support RSA encryption. Receiving agents should support verification of RSA. Signatures with key sizes 512 bits to 1024 bits. Encrypt session key for transmission with a message. Sending and receiving agents should support Diffie-Hellman. Sending and receiving agents must support RSA encryption with key sizes 512 bits to 1024 bits. Encrypt message for transmission with a one-time session key. Sending and receiving agents must support encryption with DDES. Sending agents should support encryption with AES. Sending agents should support encryption with RC2-40. Create a message authentication code. Receiving agents must support HMAC with SHA-1. Sending agents should support HMAC with SHA-1. S/MIME uses the following terminology taken from RFC 2119, that is keywords for use in RFCs to indicate requirement levels to specify the requirement level. Must. The definition is an absolute requirement of the specification, and implementation must include this feature or function to be in conformance with the specification. Should. There may exist valid reasons in particular circumstances to ignore this feature or function, but it is recommended that an implementation include the feature or function. Algorithm use decision procedure. If the sending agent has a list of preferred decrypting capabilities from an intended recipient, it should choose the first, that is the highest preference capability on the list that it is capable of using. If the sending agent has no such list of capabilities from an intended recipient but has received one or more messages from the recipient, then the outgoing message should use the same encryption algorithm as was used on the last signed and encrypted message received from that intended recipient. If the sending agent has no knowledge about the decryption capabilities of the intended recipient and is willing to risk that the recipient may not be able to decrypt the message, then the sending agent should use DDES. If the sending agent has no knowledge about the decryption capabilities of the intended recipient and is not willing to risk that the recipient may not be able to decrypt the message, then the sending agent must use RC2 or 40. If a message is to be sent to multiple recipients and a common encryption algorithm cannot be selected for all, then the sending agent will need to send 2 messages. However, in that case, it is important to note that the security of the message is made vulnerable by the transmission of one copy with lower security. Enhanced security services. 3 enhanced security services have been proposed in an internet draft. The details of these may change and additional services may be added. The 3 services are signed receipts, security labels, secure mailing lists. Signed receipts. A signed receipt may be requested in a signed data object. Returning a signed receipt provides proof of delivery to the originator of a message and allows the originator to demonstrate to a third party that the recipient received the message. In essence, the recipient signs the entire original message plus the original, that is sender's signature, and appends the new signature to form a new S/MIME message. Security labels. A security label may be included in the authenticated attributes of a signed data object. A security label is a set of security information regarding the sensitivity of the content that is protected by S/MIME encapsulation. The labels may be used for access control by indicating which users are permitted access to an object. Other uses include priority, secret, confidential, restricted, and so on, or role-based, describing which kind of people can see the information, for example, patients, healthcare team, medical billing agents, etc. Secure mailing list. When a user sends a message to multiple recipients, a certain amount of per recipient processing is required, including the use of each recipient's public key. The user can be relieved of this work by employing the services of an S/MIME mail list agent (MLA). An MLA can take a single incoming message, perform the recipient-specific encryption for each recipient, and forward the message. The originator of a message need only send a message to the MLA with encryption performed using the MLA's public key.